When designing systems in Amazon Web Services, your Amazon VPC, Virtual Private Cloud, is your network boundary. This is not just a configuration step. This is a foundational architectural decision. Your VPC defines where your workloads live, how they communicate, and how they are protected. Think of it as your private data center inside AWS. Just like a traditional on-premises data center, you define the IP address ranges, the network segmentation, the routing behavior, the security controls, and how traffic flows between components. Inside a VPC, you control the CIDR blocks. You design subnets across availability zones. You decide which resources are public, which are private, and which are completely isolated. You define routing tables to control traffic direction. You attach internet gateways, NAT gateways, or keep workloads fully internal. You enforce security using security groups and network ACLs. In other words, the VPC is the foundation of your cloud architecture. If your VPC design is weak, everything built on top of it inherits those weaknesses. If your VPC design is deliberate and well-structured, your architecture becomes scalable, secure, and resilient. As a cloud architect, you never treat VPC as a checkbox. You treat it as the controlled network boundary that enables everything else. Because in AWS, before you deploy compute, databases, or applications, you design the network. Now, architecturally, what is a VPC? A VPC is an isolated virtual network where you launch your AWS resources. Isolation is the key word here. By default, your VPC is logically separated from every other customer inside AWS. No one else's traffic touches your network unless you explicitly allow it. This isolation gives you control, predictability, and security from the start. Inside this isolated virtual network, you launch resources such as EC2 instances, load balancers, RDS databases, ECS or EKS clusters, and any other compute or data service that requires network placement. Now look at the diagram. At the highest level, you have the AWS cloud. Inside AWS, you operate within a region. Inside a region, you have multiple availability zones. Your VPC lives inside that region. Within the VPC, you create subnets that span across availability zones. These subnets determine where your resources are placed and how they are exposed. For example, in a public subnet, you typically place internet-facing components like load balancers or Bastion hosts. In a private subnet, you deploy internal services such as RDS databases or container clusters like ECS and EKS. Notice the layered structure. AWS cloud to region to availability zones to VPC to subnets to resources. That layering is intentional. It reflects how AWS structures physical infrastructure while giving you logical control. Now, what do you actually control inside a VPC? You control the IP address range, defined by the CIDR block. This determines how large your network is and how many resources you can support. You control the subnets. You decide how to segment the network, public, private, isolated, and how they map across availability zones for high availability. You control the routing rules. Route tables determine where traffic flows, whether to the internet, to another subnet, to a NAT gateway, or to a peered VPC. And you control the security boundaries. Through security groups and network ACLs, you define what traffic is allowed in and out at both the instance level and subnet level. Architecturally, the VPC is not just a network container. It is your programmable network fabric inside AWS. And as architects, we design it intentionally because every application, every database, every container cluster depends on the correctness of that foundation. Now let's talk about something fundamental to VPC design, the CIDR block or IP range. CIDR, which stands for Classless Interdomain Routing, is simply a compact way of defining a range of IP addresses. The format is straightforward, IP address/prefix length. For example, 10.0.0.0/16. Now, how do we read this? The prefix length, in this case /16, tells you how many bits are fixed. Those fixed bits represent the network portion of the address. The remaining bits are free. Those free bits represent your host addresses, the actual IPs you can assign to resources. Let's break down 10.0.0.0/16. An IPv4 address is 32 bits total. If 16 bits are fixed for the network, that leaves 16 bits available for hosts. 16 free bits means 2 to the 16th power possible addresses. That equals 65,536 total IP addresses inside that CIDR block. This is why choosing the right CIDR block size is an architectural decision, not just a technical one. If you choose a block that is too small, you restrict growth. If you choose a block that is too large, you may complicate future network segmentation or VPC peering strategies. Here's a practical way to remember it. /24. Think of it like a street. /16. Think of it like a city. /8. Think of it like a country. The smaller the prefix number, the larger the network. As architects, we don't randomly choose CIDR ranges. We design them intentionally, based on projected scale, environment separation, subnetting strategy, and long-term connectivity plans. Because once a VPC is created, its primary CIDR block cannot be changed. So this decision is foundational, and foundational decisions in cloud architecture must always be deliberate. Continuing from CIDR blocks and IP planning, the next architectural layer is subnets. Subnets are how we implement network segmentation inside a VPC. A subnet lives inside a single availability zone. That detail is important. While a VPC spans an entire region, each subnet is tied to one specific availability zone. If you want high availability across multiple AZs, you must create multiple subnets, one per AZ. Now, conceptually, a subnet is just a smaller slice of your CIDR block. If your VPC is 10.0.0.0/16, you might carve it into 10.0.0.0/2410.0.1.0/2410.0.2.0/24. Each of those becomes an isolated network segment with its own routing behavior. Let's break this down architecturally. There are typically two main subnet types, public and private. A public subnet has a route to an internet gateway. Resources inside it can receive inbound traffic from the internet if security rules allow it. This is where you place components that must be publicly reachable, such as load balancers, Bastion Hosts. These are controlled entry points into your architecture. Now contrast that with a private subnet. A private subnet has no direct route to the internet gateway. Resources inside it are not directly accessible from the internet. This is where your sensitive components live. Application servers, databases, internal services. They can initiate outbound traffic, typically through a NAT gateway, but they cannot be directly reached from outside. Now look at the diagram structure. At the top, traffic flows from the internet. It enters through the internet gateway and reaches the public subnet. From there, traffic is forwarded internally to the private subnet. For example, from a load balancer to an EC2 instance, or from an application server to an RDS database. This layered segmentation creates controlled traffic flow. Internet to public layer to private layer to data layer. As architects, we never mix these layers casually. Segmentation is about reducing blast radius. If a public-facing component is compromised, it should not automatically expose your databases. Subnets enforce this boundary at the network level. So remember, the VPC defines your network boundary. The CIDR block defines your address space. Subnets define your internal segmentation strategy. And segmentation is what transforms infrastructure into architecture. Let's now introduce an important operational and security component, the Bastion host, also known as a jump box. A Bastion host is a hardened EC2 instance placed inside a public subnet that acts as a secure entry point to access resources located in private subnets. Its purpose is simple. Private servers should not be directly accessible from the internet. Instead of exposing multiple internal machines, we expose only one controlled access point. Administrators connect to the Bastion host using secure protocols such as SSH or RDP, and from there, they access internal systems using private network connectivity. Now let's look at the architecture shown in the diagram. Traffic starts from the internet, where an engineer or administrator initiates a secure connection. That connection reaches the public subnet, where the Bastion host EC2 instance is deployed. This is the only instance allowed to receive inbound administrative access. Once connected to the Bastion host, the administrator is now operating inside the VPC network. From this trusted position, They can securely access resources in the private subnet, such as application servers or databases, using private IP addresses. Notice the key architectural rule here. Private instances have no direct internet exposure. All access follows a controlled path, internet to Bastion host to private resources. Think of this like entering a secure office building. You don't walk directly into restricted rooms. You first pass through reception, identity is verified, and only then are you allowed inside controlled areas. The Bastion host plays that reception role inside your AWS network. It centralizes access, reduces attack surface, and ensures administrative traffic is tightly controlled. In production architectures, this pattern helps maintain both security and operational access without compromising private infrastructure. The next step is understanding how resources inside a VPC communicate with the internet. This is where VPC and the internet connectivity components come into play. These components control how traffic enters and leaves your network. Not every resource should communicate with the internet in the same way. Some resources must be publicly reachable, while others only need outbound access without being exposed. AWS provides two main components to solve this cleanly and securely: the Internet Gateway and the NAT Gateway. An Internet Gateway, or IGW, is attached directly to a VPC. It acts as the bridge between your VPC network and the public internet. When a subnet has a route pointing to the Internet Gateway, it becomes a public subnet. This allows resources inside that subnet to receive inbound traffic from the internet, send outbound traffic to the internet. Typical resources using an Internet Gateway include load balancers, Bastion hosts, public-facing EC2 instances. The key idea is simple. The Internet Gateway enables direct internet connectivity. NAT Gateway. Now, private resources often need internet access, but they should not be reachable from the internet. This is where the NAT Gateway is used. A NAT Gateway is deployed inside a public subnet, but it serves private subnets. Its purpose is to allow private instances to access the internet outbound without becoming publicly accessible. For example, private servers may need to download operating system updates, pull Docker images, call external APIs, install software dependencies. The NAT Gateway allows outbound communication while blocking unsolicited inbound connections, so traffic can go out, but nothing from the internet can directly come back in. Looking at the diagram, we can see a multi-availability zone architecture. At the top sits the internet, connected to the VPC through the Internet Gateway. Public subnets in each availability zone route traffic directly to this Internet Gateway. Resources placed here, such as EC2 instances or our NAT gateways, can communicate publicly. Inside the public subnet of Availability Zone A, we deploy a NAT gateway. Now observe the private subnet below it. Private EC2 instances and databases do not connect to the Internet Gateway directly. Instead, their route table sends outbound traffic to the NAT Gateway. The traffic flow becomes private instance to NAT Gateway. To Internet Gateway to Internet responses return through the same path, but external systems can never initiate connections directly to those private resources. Across availability zones, databases replicate internally, maintaining high availability while remaining fully private. This design maintains connectivity without sacrificing isolation. Design rule to remember. A simple architectural rule applies. Public resources use an Internet Gateway. Private resources use a NAT Gateway. If something must be reachable from the internet, place it in a public subnet with an IG route. If something only needs outbound internet access, keep it private and route through a NAT Gateway. This separation is a core principle of secure AWS network design. Because good cloud architecture is not about enabling connectivity everywhere, it is about enabling only the connectivity that is required. Let's now talk about high availability and how AWS enables it using availability zones. First, a quick reminder. An availability zone, or AZ, is an isolated data center inside an AWS region. Each AZ has independent power, networking, and infrastructure. In simple terms, multiple AZs exist so that a failure in one does not impact the others. How availability zones enable high availability. High availability comes from spreading your infrastructure across multiple availability zones. If your application runs in only one AZ and that AZ experiences failure, your system becomes unavailable. But when workloads are distributed across at least two AZs, traffic can automatically shift to healthy resources. The system continues running even if one entire data center goes offline. High availability is therefore not achieved by stronger servers. It is achieved by distribution. Looking at the diagram, we see a single VPC deployed across two availability zones, AZ-A and AZ-B. Each availability zone contains a public subnet, a private subnet. At the top, incoming traffic arrives from the internet through the Internet Gateway and reaches a load balancing layer. That traffic is then distributed across application instances running in both AZs. Notice the auto-scaling group spanning the two zones. This ensures application instances exist in multiple locations simultaneously. If instances fail in one AZ, new ones continue serving traffic from the other. Below the application layer, the database tier runs in private subnets. Here we see a primary database in one availability zone. A standby copy in another availability zone. Data replication happens automatically between them. If the primary database or its AZ fails, AWS promotes the standby instance with minimal disruption. The result is continuous service availability despite infrastructure failure. Design rule. A fundamental production rule is simple. Always design production systems across at least two availability zones. Single AZ architectures are suitable for testing or development. Production systems must assume failure and be designed to survive it. Because in cloud architecture, high availability is not an upgrade. It is a design decision made from the beginning. We now arrive at one of the most important and often misunderstood concepts inside of VPC: route tables. What are route tables? Every subnet inside of VPC is associated with a route table. A route table is simply a list of rules that answers one question. When traffic wants to go somewhere, where should it be sent? Each rule contains a destination and a target. In other words, for this destination, send traffic here. Route tables control how traffic moves, inside the VPC, to the internet, or to other networks. Let's walk through the diagram step by step. Internet gateway routing, conceptually. The Internet Gateway itself enables internet connectivity, but traffic only reaches it if a subnet's route table explicitly points traffic toward it, so connectivity is never automatic. Routing decides everything. Public subnet route table. The public subnet has a route table containing two important rules: 10.0.0.0/16 to local 0.0.0.0/0 to Internet Gateway. What this means: any traffic destined for resources inside the VPC stays internal. Any traffic going anywhere else is sent to the Internet Gateway. This is what makes the subnet public. Instances here can communicate directly with the internet. Now look at the private subnet. Its route table contains 10.0.0.0/16 to local 0.0.0.0/0 to NAT Gateway. Here, internal VPC traffic remains local. Internet-bound traffic is forwarded to the NAT Gateway instead of the Internet Gateway. This allows outbound internet access without exposing the instances publicly. The local route, very important. Every route table automatically includes VPC CIDR to local. This route is implicit and cannot be removed. It is what allows resources inside the VPC to communicate with each other across subnets. Without the local route, internal networking inside the VPC would not work. It is the foundation of intra-VPC communication. How route lookup works. Longest prefix match, most specific rule wins. When traffic leaves an instance, AWS checks the route table and selects the most specific matching rule. This is called longest prefix match. Example 1. Packet destined for 10.0.1.5. The route table contains 10.0.0.0/16 to local 0.0.0.0/0 to IGW or NAT destination. 10.0.1.5 belongs to the VPC range. Both rules technically match, but /16 is more specific than /0. Winner 10.0.0.0/16 arrow local. Result: traffic stays inside the VPC. Example 2. Packet destined for 8.8.8.8. Now the destination is external. The local route no longer matches. The remaining rule applies. Winner 0.0.0.0/0. Result: traffic exits toward the internet through either the Internet Gateway or NAT Gateway. Default route table behavior. By default, subnet behavior depends entirely on routing. Public subnet, local to local, 0.0.0.0/0 to Internet Gateway. This can receive inbound internet traffic. Private subnet, local to local, 0.0.0.0/0 to NAT Gateway, can access internet outbound only, but cannot be reached from the internet. Isolated subnet, local to local, no default internet route, no internet connectivity at all. This is used for databases, internal systems, highly restricted workloads, route tables with peering and transit. Gateway route tables also control communication between networks. Traffic never leaves a VPC unless you explicitly add routes. VPC Peering example. After connecting VPC A with VPC B, you must manually add 172.16.0.0/16 to VPC Peering connection. This tells VPC A traffic destined for VPC B should go through the peering link. Without this route, the connection exists, but traffic will not flow. With a transit gateway, routing becomes centralized. The route table may contain 10.0.0.0.0/16 to local and 0.0.0.0/0 to transit gateway. Here, the transit gateway decides where traffic goes next. Other VPCs, on-premises networks, or shared services. Mental model. A good way to think about a route table is a postal sorting office. A packet is like a letter. The route table checks the destination address, finds the most specific matching rule, and places the packet into the correct outbound path. Local delivery stays inside the city. External delivery goes to the highway. Private delivery may pass through controlled gateways. Route tables don't generate traffic. They simply decide where traffic goes next. And in AWS networking, that decision defines connectivity, security, and architecture behavior. Continuing from routing and connectivity, let's now understand security inside a VPC. Up to this point, we controlled where traffic goes. Now we control what traffic is allowed. This is the role of security groups. What are security groups? A security group is a virtual firewall attached to a resource, not a subnet. That distinction is important. Security groups protect individual resources such as EC2 instances, load balancers, databases. Every connection attempt to a resource is evaluated against its security group rules. For example, in a resource security group, you might configure inbound rule port 443 from 0.0.0.0/0. This simply means allow HTTPS traffic from anywhere on the internet. That resource now accepts secure web traffic, but nothing else unless explicitly allowed. Security groups versus network access control lists. Security groups are often compared with NACLs, network access control lists. The key difference is behavior. Security groups are stateful. Network access control lists are stateless. With NACLs, you must explicitly allow traffic in both directions, inbound and outbound. With security groups, AWS automatically tracks connections for you. Stateful, what it actually means. Stateful means if you allow an inbound request, the response traffic is automatically allowed back out. You do not need to create a separate outbound rule. The connection itself is tracked. So if a user connects to your server on port 443, request comes in, arrow allowed, response goes out, arrow automatically permitted. This greatly simplifies secure configuration. Typical 3-tier setup, architecture explanation. Now let's walk through the architecture diagram. This represents a standard 3-tier application. 1. Load balancer. At the front layer, traffic arrives from the internet through the Internet Gateway and reaches an application load balancer. The load balancer has its own security group. Inbound rule: allow HTTP or HTTPS traffic from 0.0.0.0/0. This makes the application publicly accessible. The load balancer does not process application logic, it simply distributes traffic safely. Application layer behind the load balancer sits the application tier running on EC2 instances inside private subnets. These instances use the SG-App security group. Important detail: the application servers do not allow traffic from the internet. Instead, they allow inbound traffic only from SGA-LB. This means only traffic coming through the load balancer can reach the application servers. Direct access is impossible. 3. Database layer. At the deepest layer sits the database, Amazon RDS. Its security group is SG-DB. Inbound rule: allow database traffic on port 3306 only from SG-APP. So only application servers can talk to the database. No internet access, no load balancer access, only trusted internal communication. Overall flow traffic flows securely through layers: internet to load balancer to application servers to database. Each layer trusts only the layer directly in front of it. This creates strong isolation while still allowing the system to function normally. Security group anatomy. Looking at the rule structure, an inbound rule defines protocol type, for example, TCP port, such as 3306 source, either an IP range or another security group optional description. Example: allow MySQL traffic from the application tier security group. Outbound rules typically allow all traffic by default. Because security groups are stateful, outbound rules are often left open while inbound rules enforce strict access control. Security groups are powerful, but they have limits. They cannot deny specific IP addresses. They only allow traffic. If you need block lists, you use network access control lists. They cannot filter traffic between instances sharing the same security group unless you explicitly add self-referencing rules. And they do not operate at the subnet level. Security groups protect resources only, not entire subnets. In practice, security groups define who is allowed to talk to whom inside your architecture. Routing decides where traffic goes. Security groups decide whether it is trusted enough to arrive. We saw security groups, now let's see another layer of protection or network access control lists. What are network ACLs? A network ACL is a subnet level firewall. While security groups protect individual resources, network ACLs protect the entire subnet boundary. Every packet entering or leaving a subnet is evaluated by the network ACL. And unlike security groups, network ACLs are stateless. This means every packet is evaluated independently in both directions. Nothing is remembered. Stateless. What this means in practice: because network ACLs are stateless, you must explicitly allow traffic, inbound and outbound. For example, if you allow inbound HTTPS traffic on port 443, you must also allow outbound response traffic using ephemeral ports, typically ports 1024 to 65,535. If you forget the outbound rule, connections silently fail. The request arrives, but the response cannot leave. Network ACLs versus security groups. Let's simplify the comparison. Security groups operate at the resource level. Network ACLs operate at the subnet level. Security groups are stateful. Network ACLs are stateless. Security groups support allow rules only. Network ACLs support allow and explicit deny rules. Security groups evaluate all rules together. Network ACLs process rules in order. First match wins. The key capability: explicit deny. There is one major capability network ACLs provide that security groups do not: explicit deny. You can block specific IP ranges directly at the subnet boundary. For example, blocking known malicious IP ranges, enforcing compliance restrictions, adding an additional defense in depth layer. This makes NACLs useful for coarse-grained protection. Referencing security groups instead of IPs. In contrast, security groups often reference other security groups instead of CIDR ranges. This means any resource using that security group is automatically trusted. Even if IP addresses change, which happens frequently in cloud environments, connectivity continues working. This is why security groups are typically preferred for application communication. When should you use network ACLs? In practice, you rarely modify network ACLs. They are typically used for broad IP blocking compliance requirements, extra perimeter protection. For most application-level security decisions, security groups remain the primary mechanism. Mental model. A useful way to think about this: a security group is like a bouncer attached to a person. Once someone is allowed in, their responses can freely move back and forth because the interaction is remembered. A network ACL is like security at the building entrance. Every time someone passes through the door, entering or leaving, their credentials are checked again. Nothing is assumed. Nothing is remembered. Together, security groups and network ACLs create layered security. Routing controls traffic direction. Security groups control trusted communication. Network ACLs enforce subnet-level boundaries. This layered model is what enables secure, production-grade AWS network architectures. Another very important concept in modern AWS architectures is VPC Endpoint. What problem do VPC endpoints solve? Very often, resources inside your VPC need to access AWS services. For example, EC2 instances, uploading files to Amazon S3, applications pulling images from ECR services, reading secrets from Secrets Manager. Without a VPC endpoint, something unexpected happens. Even though the destination is an AWS service, the traffic leaves your VPC, goes through the Internet Gateway or NAT Gateway, travels across the public internet path, and then comes back into AWS. It works, but it is not private. A VPC endpoint solves this problem. It allows resources inside your VPC to access AWS services without leaving the AWS network. No Internet Gateway, no NAT Gateway, no public IP required. Traffic stays entirely private. There are two main types: Gateway Endpoint, used only for Amazon S3, Amazon DynamoDB Gateway. Endpoints are free and work by adding a route directly into your route table. Traffic destined for S3 or DynamoDB is automatically redirected internally within AWS. Interface Endpoint used for almost every other AWS service. SQSSNS, Secrets Manager, ECR CloudWatch, and many more. An interface endpoint creates an elastic network interface, or ENI, inside your subnet with a private IP address. Your resources communicate with that private IP, and AWS privately forwards the traffic to the service. There is a small hourly cost because infrastructure is deployed inside your VPC. Let's compare both scenarios shown. Without a VPC endpoint, an EC2 instance inside a private subnet wants to access Amazon S3. Since no endpoint exists, even though S3 belongs to AWS, traffic exits your private network path. This increases exposure and dependency on internet connectivity. Now we introduce a VPC endpoint. The EC2 instance sends traffic directly to the endpoint inside the VPC. Traffic flows EC2 to VPC endpoint to Amazon S3. No internet traversal. The communication remains entirely inside AWS's private backbone network. More secure, more efficient, often lower cost. Security bonus: endpoint policies. VPC endpoints also support endpoint policies. These policies allow you to control exactly what resources can be accessed. For example, you can allow access only to a specific S3 bucket. Even if credentials are compromised, traffic cannot reach any other bucket. This adds an additional security boundary beyond IAM permissions. Mental model: a helpful way to think about a VPC endpoint is this. It is a private backdoor directly into an AWS service. Instead of calling a public API over the internet, Your application uses an internal company network path. The service is the same, but the connection never becomes public. In modern cloud architectures, VPC endpoints are a best practice whenever private workloads need to communicate with AWS services, because secure architecture is not only about blocking access, it is about keeping trusted traffic private from the start. Now let's see how multiple VPCs communicate with each other. This brings us to VPC Peering. VPC Peering allows you to connect two VPCs privately. Traffic between them stays completely on the AWS backbone network and never travels over the public internet. Once connected, the two VPCs behave as if they are part of the same private network. Resources in one VPC can communicate with resources in another using private IP addresses. Each connection creates a peering connection ID, and routing must be configured manually on both sides. Connectivity exists only after route tables are updated. In the diagram, we have two separate environments: VPC-A, running an e-banking application; VPC-B, running another internal or government application. Each VPC has its own CIDR range. VPC-A 10.0.0.0/16, VPC-B 172.16.0.0/16 AVPC. Peering connection creates a private link between them. Now traffic can flow directly. Application in VPC-A to private network to application or database in VPC. No Internet Gateway, no NAT Gateway, no public exposure. However, communication works only because route tables in both VPCs include routes pointing traffic toward the peering connection. Without routing, the connection exists, but traffic cannot flow. Hard rules. Peering has a few important limitations. First, no transitive routing. If VPC-A connects to VPC-B and VPC-B connects to VPC-C, VPC-A cannot automatically reach VPC-C. Every pair requires its own direct peering connection. Second, CIDR ranges cannot overlap. 2. VPCs using overlapping IP ranges cannot be peered. AWS would not know where traffic should go. Third, VPC peering is not a VPN. Traffic is private because it stays on AWS infrastructure, but encryption is not automatically added. Finally, cross-region peering works, but it introduces inter-region data transfer costs. When to use what VPC peering works best when architecture is simple. For example, 2 or 3 VPCs, low operational complexity. Direct communication needs. As environments grow larger, many VPCs or hub-and-spoke architectures, Transit Gateway becomes the better solution. And when connecting AWS to on-premises environments, you typically use site-to-site VPN or AWS Direct Connect. Mental model. A helpful way to visualize VPC peering. Imagine 2 rooms connected by a private hallway. You can walk directly between those 2 rooms, but you cannot walk from room A to room C through room B unless another hallway exists. Every connection must be explicitly built. VPC peering is simple, fast, and private, but it scales best in smaller network topologies. It provides direct connectivity, not centralized networking. Continuing from VPC peering, we now move to the solution used when architectures grow larger and more complex. Transit Gateway, often called TGW. A transit gateway is essentially a regional network router in AWS. Instead of directly connecting VPCs to each other using many peering connections, every VPC connects to one central hub. That hub is the transit gateway. So rather than building a mesh of connections between VPCs, you create a hub-and-spoke architecture. Each VPC connects once, and the transit gateway handles the routing between them. With VPC peering, connections grow very quickly. If you have multiple VPCs, each one must peer with every other VPC. The number of connections becomes n times n-1 divided by 2. For example, 5 VPCs require 10 peering connections, 10 VPCs require 45 connections. This becomes difficult to manage. Transit Gateway simplifies this. No matter how many VPCs you have, each VPC only needs one attachment to the Transit Gateway. Looking at the diagram, each VPC creates a Transit Gateway attachment. This attachment connects the VPC to the transit gateway. The transit gateway itself has its own route table. This route table decides where traffic should go next, so traffic flow becomes VPC to transit gateway. Attachment to transit gateway to destination VPC Peering. Communication by associating attachments with different transit gateway route tables. This allows full connectivity between VPCs, isolation between environments, centralized network control. The transit gateway can also connect to on-premises networks through VPN or Direct Connect. This makes it a central networking hub for hybrid architectures. Transit gateway versus VPC peering. Let's compare both approaches. With VPC peering, connections grow rapidly as VPC count increases. No transitive routing, simpler but limited scalability. With transit gateway, one attachment per VPC, transitive routing supported, centralized routing control, native integration with on-premises networks. Transit gateway introduces some cost and slightly higher complexity, but it scales cleanly. When to use transit gateway? Transit gateway becomes the right choice when you have many VPCs, multiple teams or environments exist. Shared services are required. Hybrid cloud connectivity is needed. It transforms networking from many direct links into a structured architecture. Mental model. Think of VPC peering as building private roads between every pair of cities. As cities increase, roads become messy and hard to maintain. Transit gateway is like building a central airport hub. Every city connects once to the hub, and the hub routes traffic efficiently to the correct destination. This centralized model is why transit gateway is the foundation of large-scale AWS network design. And that brings us to the end of this Amazon VPC architecture walkthrough. We started from the foundation, understanding what a VPC really is, and progressively built a complete mental model of AWS networking. We covered VPC design and CIDR planning, subnets and network segmentation, internet connectivity using internet and NAT gateways, high availability across availability zones, route tables and traffic flow, security groups and network ACLs, private access using VPC endpoints, multi-VPC, communication with peering, and large-scale architecture using transit gateway. If you understand these concepts, you now understand how real production cloud networks are designed. Because in AWS, everything ultimately depends on network architecture. If this video helped you better understand Amazon VPCs, please consider liking the video, subscribing to the channel, and sharing it with other engineers or students learning cloud architecture. Your support genuinely motivates us to continue creating practical, high-quality cloud engineering content like this. Also, the complete visual guides used throughout this tutorial are available for download. If you'd like structured reference material you can revisit anytime, you can get them using the link below. They're designed to help you review concepts quickly without going back through entire videos. Thank you for watching, and I'll see you in the next cloud architecture session.